So having understood how deep submicron MOSFETs behave differently from long channel MOSFETs, now it's time to explore how this difference affects circuit design. So we designed a lot of CMOS circuits using a model that assumed a long channel transistor. Now we want to understand how different designing using short channel transistors is, if there are any differences. And so first let's draw the current IDS versus VDS for a long channel transistor and the same current for a short channel transistor. So this is the ohmic region, and then the transistor enters into pinch-off saturation, and VDS equals VGS minus V threshold, and its current is saturated. Let's draw IDS versus VDS for a short channel transistor. So again, the current in ohmic is not much different. It's smaller because the transistor is smaller. But one difference we notice is that the transistor enters saturation earlier, because the channel enters velocity saturation before it has a chance to pinch off. So we enter saturation at a lower voltage than that we would have expected if the transistor were allowed to pinch off. So saturation starts earlier than it would have, and then we notice that in saturation, channel length modulation is much more noticeable. And that's a very important difference between short channel transistors and long channel transistors. In a long channel transistor, channel length modulation is a secondary effect that could sometimes be neglected. The main cause of channel length modulation in long channel transistors is the finite conductivity of the depletion zone that forms between the end of the channel and the beginning of the drain. There's a lot more factors that go into channel length modulation in a short channel transistor, and all these factors combined together form a much more noticeable effect. And so the slope here is much larger than the slope in a long channel transistor. Also, at relatively early voltages, we find that the current of the transistor starts to increase very rapidly. So what's happening here is basically punch through. So when punch through occurs, which happens at V punch through, when punch through occurs, the transistor becomes almost a short circuit, because we have a region of very low resistivity between the drain and the source. And so we already discussed how punch through is actually a failure mechanism for the transistor. And so if we try to summarize the impacts of scaling on the transistor, we find that we have a much higher channel length modulation. So that's one thing. We find that we are dealing with velocity saturation instead of pinch-off saturation, and this leads to two effects. First of all, less saturation current, because the current is increasing with VGS, it's increasing linearly, and definitely the velocity saturation current is lower than the corresponding pinch-off saturation current. But more importantly, perhaps, we have early onset of saturation. So the voltage at which saturation occurs is earlier if velocity saturation is the dominant mechanism. Notice that when I say that the voltage at which saturation occurs is earlier, I don't mean that it is earlier in absolute terms. So if this is VSAT for the long channel transistor, I don't just mean that VSAT for the short channel transistor is smaller than VSAT for the long channel transistor. I mean that VSAT for the short channel transistor is smaller than VSAT for the very same short channel transistor if it were to pinch off. So even if we account for scaling down voltages and scaling down dimensions, the voltage at which we saturate is still earlier than would be expected. We also have a lot more leakage in the transistor. This is essentially because of drain-induced barrier lowering. So this is the main causative agent. You can argue that perhaps leakage is increasing because of more tunneling between the gate and the body, but that also happens because of drain-induced barrier lowering, because we have to make the oxide thinner in order to give the gate more electrostatic control over the channel, which is because of drain-induced barrier lowering. One thing I have to mention about transistor scaling is that at some point, the drain and the source are going to be so near to each other, and this is going to happen when we have channel length far below 10 nanometers, but the drain and the source are going to be so close to each other, then even when the transistor is cut off, we can see a tunneling current between the drain and the source. And so at some point, we are going to notice drain to source tunneling as well as gate to body tunneling. In fact, drain to source tunneling or tunneling through the channel is probably going to be the limit of CMOS scaling, because at that point, we will no longer be able to turn off the transistor. So what impact does this have on design? I would say that the major impact we have on designing circuits comes from two things: from the early onset of saturation and from channel length modulation. In fact, channel length modulation has far-reaching impacts, perhaps even more so than velocity saturation. So let's take the situation where we have a CMOS inverter, and this CMOS inverter is discharging a capacitor. So there's a V input here, and there is a V output here. And we are charging or discharging this load capacitor. It really doesn't matter. But let's assume now that we are discharging this load capacitor. So basically, we were in a situation where the PMOS was on, and then we go to a situation where the NMOS is on. And so the input voltage is changing this way. And of course, the input voltage is going to have a slope, because this input voltage is itself an output from an earlier stage. Now, the output is also going to drop with a slope, and the slope is going to be more or less the delay. Or in fact, the difference between the midpoint here and the midpoint here is going to be the delay. Now, the problem is with a finite input slope, we have a range of voltages where both NMOS and PMOS are on. In fact, any voltage above V threshold N and below VDD minus V threshold P is a voltage that allows both transistors to be on. Now, the problem with this is, assume we are trying to discharge the capacitor. So the current in the NMOS, we have always assumed was the current in the capacitor. So we have always assumed that the capacitor was being discharged by the NMOS, and that's all that was happening. But in reality, there's also a PMOS current flowing on top, because we have a range of voltages for which both transistors are on. This caused the flow of the crowbar current or the short circuit current, which was a mechanism of power dissipation as well as a reason for increased delay. Now, with more channel length modulation, we have an even further complication of this effect, because for a longer period of this range, both transistors are not only on, they're also saturated. And this means that both the PMOS current and the NMOS current are large, which means that only very small current flows into the capacitor or from the capacitor. This has a great impact on delay, and it also has a great impact on short circuit power dissipation. Another thing we have to notice is, because of the early onset of saturation, saturation occurs at relatively low voltages. And so when we are discharging the capacitor, the transistor is mostly, the NMOS transistor here is mostly in saturation. And so you will find that as V out decreases, even below its midpoint, we might still be in saturation. And this means that the saturation current is dominant in determining delay. Notice that this graph is drawn with the assumption of an infinite input slope. So the main takeaway here is that saturation current is more important than ever, because it is dominant in determining delay, and also that managing input and output slopes is more important than ever, because crowbar current is going to flow for much longer because of the exaggerated channel length modulation effect.